We have started this new series to bring stimulating and timely content to you during this challenging time. As you know, there's an acute shortage of personal protective equipment or PPE for our frontline healthcare workers. To combat this, Dr. Armani and her lab from the USC Viterbi School of Engineering devised new solutions for disinfecting existing equipment to prevent the disease from spreading. Dr. Armani's team developed a virus-busting PPE disinfectant method that utilizes UV light to monkey wrench the genetic code of the coronavirus so it can't replicate. She calls it reimagining disinfection, using the off-the-shelf items from hardware stores to make a device that can kill bacteria and viruses. In addition to this critical work, Dr. Armani holds the Ray Armani Chair in Chemical Engineering and Materials Science at USC Viterbi and also holds an appointment at the USC Michelson Center for Convergent Bioscience and the Lawrence J. Ellison Institute for Transformative Medicine of USC. She's the director of the W.M. Keck Photonics Cleanroom, as well as the John D. O'Brien Nanofabrication Library, two core nanofabrication cleanrooms at USC. Before Dr. Armani takes over the screen, please know, I think many of you were on just before we started, that if you've not yet downloaded or clicked the link for Slido, it's included. If you have a question during the presentation, please log it either in the Q&A section of the Zoom presentation, or if you're on Slido, you can send it to the Slido link. You can also vote or give a thumbs up to questions so that we can answer the most popular questions at the beginning. And Dr. Armani has already seen many of your questions as we've begun to start. So many of you have come with great questions. She will be sure to fold those into the presentation and answer those that she didn't get to at the end. So please do continue to populate those question boxes. So without further ado, please join me in welcoming Dr. Andrea Armani.
There we go. So first, thank you everyone for coming. I know it's middle of the day or end of the day, and work from home environment's always a little tricky. So doing the conventional share your screen awkwardness. So I'm going to talk about all the different strategies that are kind of being developed and emerging for disinfecting PPE, which is something that we didn't really need to think about until recently, because everybody just planned on using disposable PPE. So these two Petri dishes are kind of showing what we don't want to see, which is significant growth of bacteria, and then what we do want to see, which is when there's no bacteria growing because we were able to disinfect the agar plate and completely kill all of the bacteria. So this is, you know, the bad scenario and the good scenario. But the first thing I want to do is to thank everyone in my research group, because without my research group members, nothing is ever possible, right? A faculty member is just kind of the leader, and really the students do a lot of the work. For this specific work, I would also like to thank two key collaborating partners. So one is Dr. Rosemary Shih, and she is in the infection prevention lab at Keck. And that's where a lot of the validation tests were done. And the second is the team at S&P Engineering. So they actually built and deployed a lot of these systems. For those who don't know, USC campus right now is closed. And so in order to actually deploy systems, we teamed up with a local company in order to actually do the experiments. So this is truly one of the collaborative efforts that's happening right now in Los Angeles. So taking a step back, what is viral disinfection? So when you try to kill a virus, you look at what the different components are, and kind of there's three components that have to be functioning in order for a virus to function. And if you think about this very big picture in terms of like a cartoon, you need a protein in order to target the cell. You need RNA or DNA if it's bacteria in order to replicate, and then you need capsid to protect the virus while it's in an environment, to protect it from being destroyed. So if you're trying to destroy a virus, if you destroy any one of these things, then you can destroy the virus. So they all three present targets of opportunity when you start thinking about disinfection mechanisms or methods. So there are kind of four primary approaches. Thermal is the one that's commonly thought of first, right? Burning. Burning is always popular. And then the second approach is chemical. So this is like the hydrogen peroxide or chlorine treatments. So, bleach as well, like the Clorox wipes, which are very popular. And then the second two are UV and ozone. So ozone is obviously not good for the environment, but it is very, very effective because it actually targets all three, right? So it targets DNA, the protein, and the capsid. So it completely destroys a virus. UV actually destroys two of the three, right? So it destroys the capsid and the RNA. So it targets two of the three. It doesn't kill the protein. But in the process of destroying two of the three components, it does a very robust job of killing viruses. So that's why UV is desirable. But it's not just UV, UVA, UVB, UVC. It's actually specifically UVC. And we'll talk about why in general. However, UVC has been used well before COVID, and it will be used well after COVID. And it's important to note that, we shouldn't be completely focused just on today's threat. Actually, there was an antibiotic resistance threat report that came out by the CDC in December. And it really focused on the fact that antibiotic resistance in hospitals has actually gone down. Even though antibiotic resistance as a disease is still an emerging threat. And the problem is antibiotic resistance has now spread into the community, which means around us. So even though kind of the general thought is that antibiotic resistant and antibiotic resistance bacterial infections are, primarily something you catch in a hospital or in a healthcare setting, that's actually no longer true. So when you're thinking about disinfection, it's not just disinfection for viral diseases. It's actually now a bigger concern for disinfection for antibiotic resistant bacterial and fungal infections. So the idea of, increasing our methods is actually going to be a concern forever going forward in order to combat things like antibiotic resistance bacterial infections. Not that I'm trying to scare everyone, but this is just something to remember. So the reason why UVC is great is because it can actually target both DNA or bacteria as well as RNA, which is viral infections. And how it works is it actually targets a very fundamental component of both, right? So it doesn't target a protein, which could be specific to one or the other. It targets the fundamental building blocks of both components. So it targets something called the pyrimidines, which for those of you who remember biology, which don't worry, because a lot of people don't, they're the, T, C, and U parts of the RNA and DNA. So they're, two of the four building blocks. And what happens when you expose it to UVC wavelength is instead of, UT binding with each other, suddenly they bind with themselves. So you end up with these dimers. So instead of having DNA where you have these nice little bridges going across, suddenly they form kinks. And because they form kinks, the DNA or RNA can no longer replicate. So it fundamentally inhibits viral or bacterial replication. So it's a fundamental kind of stop to bacterial and viral replication, which leads to death. And that's good because it's death of a bad thing. So when you're looking at, how this is typically implemented, UVC and as a method has been around for a while. So a conventional UVC system in a hospital looks, I describe it as like a toaster oven. However, instead of a heating element, there's UVC light bulbs. And they're typically designed to be small. So you can see, the size of the person's hand here. And you can put in like small medical instruments, maybe surgical supplies. You put them in, close the door. It's truly a single button. And get out, and it's been cleaned. There are larger systems, so these are typically found more in research labs, and these are biosafety cabinets where you can do cell culture, things like that, and they will have an automated cleaning cycle built in. So when a person walks away, you can hit a button and it will automatically expose the entire interior of the chamber to UVC. And this is also designed to, clean and disinfect the entire system. Now, one of the questions was what type of fluence is needed. So the fluence is actually a known factor. So how I determined my fluence was I looked at the EPA and FDA guidelines. And the EPA and FDA guidelines are, a dose for a virus is around 100 millijoules per centimeter squared, and the dose for bacteria is around 10 millijoules per centimeter squared. Now, the reason why there's a factor of 10 difference there is bacteria are double-stranded and virus is single strand, right? So there's half as much. So the thought is that you need 10 times more. And the thought there has actually been proven out. The EPA and FDA have done extensive tests. So actually in a lot of water systems, they actually use UVC as part of a sterilization kind of stepping stone. So that's why, the EPA is involved in this, because it's actually used to clean our water supply. So I didn't do experiments trying to determine what the intensity should be. I looked to the government to determine what they said the intensity should be. So even though there are these existing systems, typically what happens in an existing system is you will have all of your UVC located in some sort of primary disinfection hub in an established medical facility. However, as we all know, a lot of times, for example, like right now, those primary hubs are not necessarily located near where disinfection is needed. For example, right now in Central Park, there isn't a primary hub, right? Where there are tents, yet disinfection is still needed at that site. So we wanted to create something that could be lightweight and inexpensive, very fast to manufacture, right? Like putting up all of these tents for patient care was very fast to manufacture and very fast to deploy. But similar disinfection systems are not equally fast to manufacture and deploy. So we wanted something that could mimic that and still provide healthcare workers the disinfection that they needed. But yet it also needed to be able to hit this 100 millijoule per centimeter squared intensity in order to be useful. And this 100 millijoule rate had been shown to give a 3-log reduction in growth, which is, again, that FDA standard. So those were kind of our design criteria. So how this is achieved and kind of the 3 key components was to have like a portable empty bin, and that would act as our enclosure, a UVC bulb, and then a reflective interior coating. And the role of the reflective interior coating is very important and should not be underestimated. And the purpose is that if you don't have a reflective interior coating, if you remember light being particle or wave, the light comes out of your light bulb and will hit the opposite side. And if there's no reflection, it stops. Now, if you have about 66% reflection, it will bounce off of the other side and come back and then continue to bounce. So you can get multiple passes and you will have a higher probability of your light interacting with whatever is in the middle. So it basically acts as an amplifier of your initial starting optical field. So it allows you to have a single light bulb or a single light source and still get a higher effective intensity of power inside your chamber. So then the question becomes, will any reflective surface work? Do some of them have higher reflectivity at UVC wavelength? And it turns out that chrome spray paint is actually, it gets its chrome color from having aluminum flakes inside the chrome spray paint. And aluminum at UVC wavelength is 90% reflective, which is very high. So we simply spray painted the inside of our bins with chrome spray paint, specifically Rust-Oleum chrome spray paint, if you're interested, which you can buy at Lowe's. So that was a very simple solution to what could seem to be a complex problem. We then took and wanted to do a test system on face shields. Obviously, face shields are not easily able to be acquired. So then we decided to use plastic petri dishes, which are made from a similar plastic as our mimic for face shields. We used a bacteria called Bacillus cereus as our test system. We chose this because it's a gram-positive, endospore-forming, UV-resistant bacteria. So all three of those things are key components, especially the endospore-forming. So endospore-forming means that it is when it's put on this plastic surface, it basically self-protects. So that makes it much harder to kill with UV light. So we basically raised the bar on trying to actually kill our bacteria. Then after we did the exposure to the UV light, we put it on agar plates, which is basically we gave it food. And we put it in an incubator in a nice, moist, humid environment. So we basically tried to make it grow. So we tried to encourage the bacteria proliferation. So after 24 hours of being in this nice, humid, warm environment, if we didn't expose it to UV light, we had, a lot of colony forming units, or CFUs. And this is an example of that plate. So essentially our bacteria were really healthy, happy in their nice incubator. If we exposed it to 1 minute, our number of colony forming units dropped by at least 3 logs, and we had 3 samples, 3 separate petri dishes inside our box, dropped by at least 3 logs, or it was undetectable. If we exposed for 3 minutes, we had no cells or no bacteria inside our box. And at 6 minutes, we had a few, but we couldn't really, detect any in the other 2 samples. So we were able to get to 3 log reduction with 1 minute exposure. But what we've, told people who've used our system is, just to be safe, they should do 3 minutes. So, now that we have this system, what should we do with it? So the first thing we did is we gave it to a few of the physicians around LA. And then we also gave some PETG face shields. And this kind of allowed a mini ecosystem to be created, right? So the PETG face shields can be cleaned inside the box when you combine it with a chemical wipe. Right, so you now have a primary chemical wipe, you have a secondary with a UVC, and so this creates kind of a nice ecosystem of being able to reuse your face shield with a UVC system. But word got out, and then we had to, increase manufacturing capabilities, which as a faculty member was quite the experience. And so, as I say, this is kind of the true meaning of the Trojan family. A lot of Trojans around the world and, in the SoCal area suddenly started emailing me. And, we've made something like 50 or 60 of these boxes now, several hundred face shields, and deployed them. And now we're beginning to move outside of USC to send to, the Army, as well as other groups in India. And then, long term in the future, again, we're looking to, explore other options, right? Instead of just having, a fixed box, as great as it is, think about, if you have conveyor belts, instead of just looking inside with x-rays, could we retrofit this, and do, both x-ray as well as cleaning while it's going through. And then we actually just started a collaboration with SK Gupta on trying to come up with a more intelligent way of having robots. So you may or may not have seen the large robots that have mounted on the surface, 6 to 12 UV vertical bulbs. And I like to refer to those as like the UVC Roomba systems, because they basically will go around a space and just clean anything that's a superficial surface, right? But if you need to like move a book or, get behind something, those systems aren't able to do it. Whereas if you have a robotic system, it can move things and get behind things. So it's much more interactive and engaging. So we're looking to create this type of system that can both do that superficial, broad spectrum cleaning, as well as actually interact and engage with the environment. So I'm very excited about this. I've never done robotics, so it's a new area for me. And again, I'd just like to thank all of my students and answer any questions you may have. So I'm going to stop sharing and go through questions.
Thank you so much again, Dr. Armani, for that presentation this morning. I know we had quite a few people call in during the session as well. So just as a reminder, you can post your questions here in the Q&A or in the Slido link that you were sent. So we have quite a few questions coming in, and I'll start to send those your way. You can also see some of those as well. And I know that many people are concerned about the care for healthcare workers. So they're concerned about how does this PPE or personal protection equipment become clean so that these healthcare workers can remain at work and help all of us. There are some questions around that, and also questions about our own protection. How can this be pivoted and used at home? So I know that there are quite a few on Slido about, how can this be used? I know I purchased online my own
Wand.
Soap. Yeah. We had a question about, phone soap, which is a box the same. Yep. Mine came with very dangerous and scary warnings about home use. So I'd love for you to take us through, and I think that'll answer a few questions about how can we pivot and use this, or should we at home, and do these commercially available products, are they useful?
Yep. So there were a lot of questions wrapped in there. So I'll try to go through them. So I'll go in reverse order. So for example, that phone soap box is a UVC system. And so it's the exact same wavelength. So it's at 260 nanometer wavelength. So it operates the same way. It's still killing the, still reconfiguring the RNA and DNA. It comes with a lot of very scary warnings, but then, your, bathroom cleaner comes with a lot of scary warnings, right? Anything that's going to kill a virus or kill a bacteria is also going to kill your skin cells. All right, it's not specifically targeted for one thing. So that I would say gets to the question about, can this hurt you, right? UVC wavelength is bad for you, right? Just like UVA and UVB wavelengths, which give skin cancer, UVC has similar negative effects, right? So you would never want to try to disinfect yourself with a UVC bulb. Right, that would be a very bad idea. That would have very bad health side effects and health consequences. So you could think about using something like this in an at-home setting. There would need to be safety precautions put in. So for example, anyone who's ever had like one of those like antique jewelry boxes or music boxes where if you open the lid, it then triggers the box to like turn on and start playing a song, or if you've even seen one of these in like a museum. So that is basically like a safety mechanism, right? So you could imagine having something like that in a UVC system where if you, basically the inverse of that, but where if you open the lid, the UVC light would automatically turn off. So it wouldn't be possible to, have the box open and the light on. So you could do something along those lines. That would be one strategy of having an at-home system. You wouldn't necessarily want to have an at-home system like the handheld wand, which is commercially available. So there's an at-home wand where it has a low intensity UVC bulb and you can move it very, very, very slowly across surfaces. I believe you hold it for like 30 seconds over a surface. And so there's kind of a trade-off between the intensity of the UVC source and how long you have to hold it over a surface in order to have it actually be effective. So that's kind of the alternative route. You can imagine having a box you can put things in, and you can have a really low power source, but you have to leave things in the box for like 8 hours. Um, and that's kind of how the phone soap works, is you have to leave it in there for like 6 hours, I think. I don't have one.
Thank you. I'm deciding if I'm going to use mine or not. I think a few other people were as well. So there were some other questions about I sort of alternate sources for this type of disinfecting and autoclaves. Someone
Yep.
mentioned that they read that they can turn their Instapot into an autoclave. Um, you're really looking to source these to help healthcare frontline workers, and those face shields that you're looking to reuse are very large and hard to manufacture as quickly as they need them, so that they can have fresh shields. So I don't know if you want to talk a little bit about home use or autoclave, or why you maybe chose this over that. You got to that a little bit with the biology lesson at the beginning, but maybe you could speak to that.
Yeah. So I would say we got to it initially because it was posed to us as a problem. So you can use autoclaves with face shields. You can use autoclaves with some materials. So when you're thinking about disinfection, it's the appropriate disinfection for the appropriate type of material. So not every disinfection method works with every type of material. So you can't just choose one disinfection method and apply all. Right. So if you even think about like your home cleaners, you have home cleaners for your oven, you have home cleaners for your bathtub, you have home cleaners for your wood floor, right? You wouldn't necessarily want to pour bleach on your floor if it's a wood floor. If it's tile, knock yourself out. So it's the same thing when you're thinking about disinfecting. You can't necessarily use an autoclave on every single material. So like an autoclave has been shown to be very, very effective on steel, but on paper it doesn't work as well. So that's where a UVC can come in handy as a complementary, right? You always want to have like a toolkit. There isn't a one size fits all. So that's where you need to be able to have alternative sources. And I can't make any comments on if the crock pot works or not. I haven't tried that, so okay. I don't know.
I'm using mine every day, but not for that.
Okay.
So we had a few more questions about that. Someone asked, how many face shields does your device hold? Okay. How long does that take? So we know the turnover is, and I know that you talked specifically about the UV light being specifically able to work with the surface of a face shield, which is a very specific surface. But someone did ask if this could be applied also to the sort of material or paper N95 masks that we know are also in great shortage.
So let's see. So our system right now, so like the boxes that we use, our system can hold 3 masks or 3 face shields at a time. And it takes, we suggested 3 minutes. So it's basically a minute per shield, which is fast-ish. So we designed with that metric in mind because the current UVC systems at most hospitals, it's a minute. So we wanted to have something that ideally was a minute. So we decided, a minute per shield. Hopefully everybody would remember that. Just like with the home use systems, we have warning signs everywhere on them. We also imprinted the specifications everywhere on them. Trying to remember your second question. I was accepting questions at the same time.
Oh, it's about the face mask, the N95s.
N95s
on that type of material, or this. I mean, you said this is a specific solution for a specific.
Yeah, that is an active area of debate. So there are some studies that have shown that UVC, even as a general method, there are some studies that have shown that UVC can work on N95. There are some studies that have shown that it cannot work on N95. So there's kind of there's two different issues, right? So you have first the, can the UVC light actually penetrate into that like fibrous filter paper network? With a transparent face shield, there's no problem because the UVC light can penetrate, can kill all the viruses, there's no question. But with an N95 mask, it's an opaque system, so it really gets to, how efficiently can the light actually penetrate into that fibrous network. So that's question one. Question two is, how does repeated exposure change the mechanical stability and strength of that fibrous network? Is it going to make it more mechanically stiff and then more prone to cracking? And then once you have cracks in it, it's not going to be a filter at all, right? You're just going to have these gigantic holes. So there are some studies showing that you can use UVC to disinfect and then it still works and it's great. And then there are other studies showing that you can't. So we haven't tried to do it. That is still something that we're kind of monitoring what other studies are showing, simply because it's such an active area of research. And it's something I wouldn't really feel comfortable recommending until it was more definitive.
Thank you. So the other question, and I know that you've been thinking about how to disseminate this because you want this widely used and you have it patented and really want to make sure it can be in wide use. So we've had a couple questions about, is there a how-to guide? Is this something you'll be sharing? How can I get this for myself? How can you tell us a little bit more about how you see this rolling out, and if folks on the call or others can get step-by-step instructions?
So first off, if you want step-by-step instructions, you can go to my website, and I posted something on Archive. So if you're familiar with any kind of academic journals, Archive is basically a preprint server. So you can download for free anything on Archive, and I included basically detailed schematics. I actually included parts lists. I included vendors. So effectively a bill of materials of exactly what I used. I also included calculations on, if you couldn't get a bin that was, 3 feet by 4 feet, if your bin was 2 feet by 3 feet, how you would need to adjust the intensity of your bulb. So like the entire matrix of variables. And that's on my group website, which I'm sure Marianne can share that information with you. But it's just armani.usc.edu. So, and then how do I see it rolling out? So right now we're just really focused on trying to get as many systems to healthcare workers. And again, and then we recently, again, because we sent a system to Afghanistan, because one of my faculty colleagues who's an MD is actually currently stationed in Afghanistan. So he's a reservist. So he's head of one of the ERs at a base there. And he emailed me and asked me for one. So we sent one to a base in Afghanistan. So we've now, and then because of him, now more bases want one. So we've now kind of branched out from just focusing on US hospitals. And again, we're donating. So everything we're doing is donation based. So we aren't charging.
Thank you. And thank you for making it open source and available. That's really fantastic.
Yeah.
Someone had a question about approximate cost to build one box.
Yeah. So we got, I can tell you. So we got the tubs from Lowe's or hardware store. They're like their standard plastic tubs. I think they were like $15 each. The bulbs were like $18. The mounting bracket was like $12. So it was like $15 all in. That was the spray paint. I think the spray paint was like $15, but then the spray paint, we've only used one can of spray paint so far. So if you amortize that cost, it's like 50 cents, kind of in the noise.
Very reasonable
yeah.
to disinfect. We had another question about the study. So Fred had asked, any studies on dose dependency versus wavelength?
Oh, So there haven't been any studies on dose dependency versus wavelength. So again, we're using a bulb, right? So normally when you think of a light source, there are two types of light sources. You can think of like a laser, which is a very narrow line width fixed wavelength light source. So that might be like 260 nanometers plus or minus 1 nanometer. And then you'll have a bulb, like a light bulb, which is broad spectrum, right? So that might be like 180 to 300 nanometers. So very broad spectrum. And we haven't done any kind of studies on, the laser variant simply because, sorry, simply because a bulb is much cheaper than a laser. And we were looking to optimize cost and get a system that was as cheap as possible. However, it is known that DNA and RNA, that reaction that actually causes the transcription to be inhibited is dependent on it having very high optimum absorption, and that peak absorption wavelength is at 260 nanometers. So I would anticipate, but that's not like a 260, delta function. There is like a curve to that. So I would anticipate if you're around 260, you're going to be fine. But if you try to use like a 600 nanometer light source, it's probably not going to be effective. Mary, you're muted.
Thank you. I'm still learning to use this as well. I've never had this many people in my living room, so it's a little tricky. So a couple of folks have asked again about other systems, and I know this is really something that you can speak to as well, most likely. But there are questions about this chlorine dioxide used to clean the Diamond Princess and the Orleans Parish prison. So these are larger scale and very different surfaces. Maybe you can talk a little bit about how that works and how that's complementary to this type of disinfection.
Yep. So hydrogen peroxide falls under that chemical treatment. So it's a very different type of treatment, and there's actually two different ways of applying a hydrogen peroxide treatment. So there's using an actual liquid hydrogen peroxide. So you can imagine putting hydrogen peroxide on like a wipe and manually wiping down, or doing a vapor hydrogen peroxide treatment. So if you remember, or if you've been looking in the news recently, Battelle just made a chemical vapor hydrogen peroxide modular unit that they're just now beginning to deploy, primarily on the East Coast. Battelle's located in Ohio, so it makes sense that they're kind of emphasizing that way. And this modular chemical vapor hydrogen peroxide system can treat thousands of N95 masks per day. Again, because it's vapor and chemical, it's able to permeate into a fiber network. In their system, they've optimized it specifically to do N95 masks, and that's all they're treating is N95 masks. So they aren't looking to treat anything else, not gowns or face shields or anything like that. So they've really focused in on masks. So it's, again, the hydrogen peroxide basically goes in and destroys the capsid and the protein, not the DNA or RNA.
Thank you. So we're getting a few more questions in about the volume of the box, which we did get into a bit, but once they're packed in, do you need a line of sight?
So yes and no. So you need a line of sight, especially if you don't have any kind of reflective surface. Right. So if it's only a single pass system, then you need to make sure you definitely have a line of sight. If you have a reflective surface, then as long as your photon doesn't interact with anything on the first pass, then that's where having a reflective surface, especially reflective on all four sides, really comes into play. And if you have a highly reflective surface, which is why having aluminum with 90% reflectivity really helps, because then your photon is basically going to be confined inside a literal box and bounce around until it gets absorbed by the thing you're trying to disinfect. So that's kind of why the optimization of having this highly reflective box containing all your photons can be a huge benefit.
And then we have had several questions about the cost and how these will be disseminated, but we did have one more about someone focusing on commercial use, and is there more data you can introduce on operating, like the size? We did talk about time for operating was about a minute per mask. If you put 3 in, it take about 3 minutes. But do you have any other anything else you want to say generally if people want to make these and use these? Is there anything else that they should know, or another site to which you can direct them for some specific data?
So about, the size. So again, the size is going to scale with the intensity of the bulb you use. So if you try to have a larger volume system, then you're going to need a more intense bulb. Now, as far as a site I can direct you to, again, I would direct you to either the archive article that I posted, which is on my website, which has a lot of information. I know USC also wrote a press release about it, which has more bigger picture information. So that has like a more general overview, which might be helpful. And then as far as like commercialization, right now, I'm honestly not thinking about it. I'm really focusing on, like December. So that's honestly my main goal right now.
Thank you. We just have a few last questions,
Mhm,
and then if you have anything that this has brought up that you want to let us know
mhm,
before we wrap up, just to be cognizant of everyone's time.
mhm.
Um, Someone just asked where in the website is the paper. We can send you that
Oh,
information as well.
I can tell you. So it's actually two places. It's a really easy question. So on my website, if you go to the right-hand side, there's a list of like recent publications. And then I think it's like the third one down. And it says like build at home UV disinfection system, and it says link to archive. And then also at the bottom, there's a link of like current COVID-19 activities going on in the lab, and then there's a link down there. So it's actually two places.
Wonderful. Thank you. Last couple of questions. People seem to have several questions on Slido about, we're all concerned about our own personal use of personal protection. Masks that, as you say, are cleaned differently. There were several questions. Can I microwave it, leave it in the sun, put it in a bag for a few days? Sort of how do I turn over my own personal PPE now that it's being required in places where you shop or gather or would pass people,
Yep.
someone runs past you in the morning and you don't want to get that side stream. Can you give us a little bit of your thoughts about the best way to handle our own at home?
Yep. So, I mean, there's obviously, a huge shortage. And so having, trying to come up with a strategy for, reusing PPE is challenging. And putting it in a bag and, waiting like 72 hours is one approach, because it's thought that the virus doesn't, last more than 48 hours on most surfaces. So that's one strategy. If you're going to go that route, you also need to make sure that, if there's multiple people in the household, that like you aren't reusing the PPE from somebody else in the household. So, that gets to like labeling your PPE, so that you don't wear your, husband's or wife's or daughter's mask. So that kind of adds like another level of complication. Depending on what your mask is made of, then you can start thinking about microwaving, which can be very effective for bacteria. So that can be kind of like a secondary disinfectant method. Microwaving, it hasn't necessarily been shown on COVID-19 yet. There's some preliminary studies, so I would have a hard time definitively saying it would work. And again, it would also depend what your mask material is made out of. So usually when you do a microwave treatment, you put like a vapor in there, like some sort of water, so that you can actually excite the material. But then again, doing that with a paper mask, not ideal. And I'm assuming paper masks. So it's what we're doing in my household, which might be helpful, is we basically have a room that we have just allocated to being the dirty room. And that's where everything goes and hangs out for 48 hours. All of our mail, everything goes in there.
Great. That's a great tactic. Thank you for sharing that with us this morning or this afternoon. Do you want to say anything before we have a little bit of information to share with everyone about our next webinar series? But do you have anything that you want to share about your partnership with KEC and your other partner? And is there anything you want to say about, did you have to get some approval process or anything you want to say kind of to wrap that part of that for us?
I mean, first, like USC has been a great teaming partner, you know, and there's an amazing collaborative effort going on right now at USC, you know, between the engineering school and the KEC researchers. So KEC basically holds, you know, like thinking workshops and challenge workshops where they basically throw out problems, and then the engineering school, you know, tries to come up with solutions. And then KEC is doing a fabulous job of helping us validate the solutions. Because at a lot of institutions right now, the engineers are doing a great job of coming up with solutions, but they're having a hard time actually validating them. So actually having that partnership with the medical school has really been invaluable in actually seeing this move forward. And I would say, you know, kind of building on that, I was able to do this without asking my students to return to the lab, which was really helpful. Because right now I don't want to ask my students to go back into the lab. So I was able to build this working with a local company that actually is a defense contractor. So they're in business right now because they're building missiles. So they were able to do this, you know, they volunteered to do this in their evenings and weekends. So they built them, and then I personally drove them over to KEC, and then all the lab technicians at KEC actually ran the experiments. And my students did all the theory. So we were able to do this without exposing any of my PhD students back to campus, you know, potentially exposing them to COVID. So it really was this, you know, LA-wide symbiotic effort, which was really nice to see. I will hand it back to you, Marianne. And you're on mute again.
Thank you. Trying to get it back. Thank you so much. And it really shows the power of that bench to bed ability that we have at USC with partnerships, collaborative partnerships with public and private partnership, as well as with our medical school. So thank you so much, Dr. Armani, for joining us live today and for answering all of these questions. If you didn't get your question answered, we will be able to send you answers to your question, as well as give you additional information. This was streaming on YouTube. We're also recording, so if you want to refer back, you can certainly do that to get any of this information. So that will be available soon. We hope that you can join us again next week as we host a follow-up to the USC PPE workshop. Also this Friday, we'll pivot from PPEs to social media in a session called Charting COVID-19 Chatter on Social Media by Emilio Ferrara. More information can be found in our online events page, and it'll be pasted here in the chat box as well. So we hope that you can join us again. Hope you all stay well. Please be safe and fight on. Thank you again.